Hymers. I'm from the philosophy department at Dalhousie. And my task today is to introduce to you Mary Domski, who is Associate Professor of Philosophy and Chair of the Philosophy Department at the University of New Mexico. She received her PhD 10 years ago, working under Michael Friedman on geometry and experimental method in Locke, Newton, and Kant. In the intervening time, she's published over a dozen papers on Descartes, Kant, and of course Newton. And today she's going to talk to us about philosophy of science in Newton's general scholium.
All right, thank you. There's a one-page handout. Anyone needs one. So I get the lucky job of discussing these 4 sentences that have been widely discussed the past 300 years. And I'm going to set myself the possibly impossible task of trying to understand what Newton means by deduction from the phenomena. I feel like I'm trying, excuse me, to cover a lot, but I framed the talk to try and get feedback because I need feedback and help to see where my reading might be wrong, is one way some of you might put it. So just a couple remarks to get us going. What's clear from those 4 sentences, which you have on the handout, that there's a rejection of hypotheses by Newton, and that also there's this essential link between an experimental philosophy that he's talking about and claiming to practice, and also deducing or a deduction from the phenomena. Now, there seems to be, what's unclear, of course, is what it means to deduce from the phenomena from the 4 sentences, that we seem to have an important clue at the end of those 4 sentences when he talks about the 3 cases, the qualities of bodies, which are discussed in Rule 3, the laws of motion, and the law of gravity. There's a handout for those kind of. So not everyone has found the clue very helpful, and one person in particular, Alan Shapiro, has commented that here with these 3 cases, Newton is mixing 3 very different kinds of principles: universal qualities of matter, the laws of motion, and a sophisticated mathematical theory. These are, according to Shapiro, such heterogeneous cases that we should not expect one method underlying their demonstration. So what Shapiro famously does, is you're mostly aware probably, is he looks at the slogan deduction, I think. Yeah. He looks at the slogan deduction from the phenomena here on the bottom as communicating a set of philosophical commitments. And what he comes to as a conclusion is this last statement in boldface: we ought only, this is Newton's commitment, we ought only forward conclusions that are grounded on or argued from the phenomena. So the way Shapiro reaches this conclusion is by looking at commentary written around the same time from the optical papers, as well as from the controversy with Leibniz. So really my task today is to try and improve upon this reading and to get a better handle on what it means to say that we should do this, namely forward conclusions or propositions that are grounded on or argued from the phenomena. The way I'm going to do it, though, is following Andrew, so it's good that I come after, is not to look at Leibniz, but to look at Descartes. Before I get there, this should be on the handout, what I say here in the next couple slides, so you can refer back to it. So what I want to do is look at the 3 cases and try to improve Shapiro's reading. And I'm trying to identify a peculiar function that the phenomena play in Newton's experimental philosophy. And so let me just note, as Shapiro, I take phenomena in the broadest sense as empirical evidence. And so here, this is the claim that I'm trying to make. In each of these 3 cases, the phenomena serve to justify the applicability of mathematically certain and rationally intelligible principles to the physical system, or put differently, the phenomena bridge the mathematically certain and rationally possible order of things to the empirically actual state of affairs. And again, my strategy. I'm going to draw on Descartes' principles of philosophy, and part 3 in particular, because this is where Descartes uses hypotheses and phenomena. And I'm going to try and use that section to help understand what Newton means by hypotheses and how Newton tries to improve upon Descartes' hypothetical natural philosophy. So many people here have talked about the anti-Cartesian stance that Newton takes, but I think I'm doing something a little different insofar as I want to say that there's a fundamental similarity between their approaches. And so in particular, and this is on your handout as well, so you can refer back to it, Newton subscribes to the same general methodological framework as Descartes, according to which we are to begin our investigation into nature by identifying principles that meet the standards of reason, and that's a phrase from Descartes, that are rationally intelligible. And what Newton does now is improve upon Descartes' approach, this hypothetical approach, by relying on empirical evidence to fill in the Cartesian gap between intelligibility and actuality, or more generally, between explanation and truth. So as the story plays out, what I'm emphasizing in Descartes is you have explanation without truth, and this is precisely what Newton is trying to improve upon when he presents his mathematical principles of natural philosophy. So, the outline of the talk. Start with Descartes, and then get to Newton's three cases, but given the constraints on time, I'm not going to talk about gravity, and I actually, for time, and because I think for me the hardest case for my reading is the qualities of bodies. So I want to make sure I get to the cases that I will likely need the most help with. And so, to Descartes, so I know I'm going to say a lot of things you already know, and so I'm hopefully give some new life to old texts and connect them in a novel way. Part 3 will be my focus. I don't really need to remind you of this, but of course, once we get to part 3, we already have the 3 laws of nature. We have a bunch of medical truths about God and soul and body and space and motion, etc. The goal of part 3, recall, according to Descartes himself, we must now consider whether we are able to explain all the phenomena of nature by the certain principles concerning material things, namely by the 3 laws of nature, which were identified in part 2. To do so, we must begin with those phenomena which are the most universal and on which the rest depend, namely the general structure of the whole universe. So, as you're all well aware, what he begins with are astronomical events, or planetary motion, the sun, the stars, etc. And the way he starts is by presenting the phenomena that are to be explained. So just some of the ones he mentions in the first few sections: the distance between the heavenly bodies, how they shine, whether by their own light or not, and the relative distance between them. So just bear in mind, because it'll be important for my story, that the phenomena for Descartes are effects, and the goal is to identify the principles or causes that explain what we observe, namely the effects or the phenomena. And as he does so, it becomes clear that we need to deduce the phenomena from hypothetical causes or hypotheses. And so as he brings forth the theories of Ptolemy, Copernicus, and Tycho, he tells us quite explicitly that they are hypotheses. And what he means by this, so the second passage here, they explain the phenomena without considering whether their proposals conform to the truth. He's consistent about this throughout the presentation. And then he says, considered purely as hypotheses, their theories explain the phenomena equally well. Now, of course, it's at this juncture that he presents his own hypothesis, the vortex hypothesis. And the reason we're supposed to accept his over these others is not because it's truer, but because it's a better hypothesis. So he says, I shall set forth here the hypothesis which seems to me the most simple and most useful of all, both for understanding the phenomena and for inquiring into their natural causes. And yet I give warning that I do not intend it to be accepted as entirely conformity with the truth, but only as a hypothesis or supposition which may be false. So what he emphasizes throughout, in the few passages he talks about this, is the greater simplicity and usefulness for understanding that we can ascribe to the vortex hypothesis. This is what makes it better than Ptolemy, Copernicus, etc., and Tycho. So after, and I'm not going to read through the whole passage, but after he presents the details of the vortex hypothesis, he says, for by that alone and without any other devices, all their phenomena are very easily understood. And so it's simpler in that, on the one hand, it's less complicated, and on the other, that it assumes the least. There's a very simple structure that he's proposing, and from this, he can now explain the other phenomena of the heavens, as he sets out to do in the next several articles, or sections of part 3. And throughout, so even beyond this, after we get to around Article 40, he still emphasizes this distinction between hypothesis and truth, and explanation and truth. And so at one point, section 43, he has this claim that it can scarcely be possible that the causes from which all phenomena are clearly deduced are false. And certainly if the principles which I use are very obvious, if I deduce nothing from them except by means of a mathematical sequence, and if what I thus deduce is in exact agreement with all natural phenomena, it seems that it would be an injustice to God to believe that the causes of the effects which are in nature and which we have thus discovered are false. For we would then be accusing him, God, of having made us so imperfect as to be liable to make mistakes even when correctly using our reason. So it sounds as though here he wants to say, look, if what I deduce matches the phenomena, consider it true. Very quickly, though, but please don't, that I nevertheless wish those causes I am proposing here to be taken only as hypotheses. I wish what I shall write later to be taken only as a hypothesis. Skipping down, I shall consider that I have achieved a great deal if all the things which are deduced from them are entirely in conformity with the phenomena. For if this comes about, my hypothesis will be as useful to life as if it were true. This qualification again plays out in the rest of the principles where he proposes or tells us what the truth is versus what he's going to offer us in the natural philosophy, his natural philosophy. And namely, what's true is this. What the Christian faith teaches us and what natural reason convinces us, namely that the world was created in the beginning with all the perfection that it now possesses. Because taking into account the omnipotence of God, we must believe that everything he created was perfect in every way. This he calls or considers the true account of how nature came into being. But what he wants is an explanation, a natural philosophical one. So we can't stop here. What we want to do, again, is explain or understand how causes give rise to effects. So what he proposes in this important transition section of 45, he proposes principles that are simple, easy to know, intelligible, from which we can, in some mathematical sequence, go from cause to effect. So this line, again, it's hypothetical. He's offering hypotheses or devising some principles which are very simple and easy to know, by which we can demonstrate that the stars and the earth and indeed everything which we perceive in this visible world could have sprung forth as if from certain seeds, even though we know that things did not happen that way. And what he offers in particular, so we already have the vortex hypothesis on the table, he offers these hypotheses about how God created the world. Again, though, we already know the true account. God created everything as perfect in every way. But he gives us these three hypotheses in section 46, that there's an equality in the original size of matter, an equality in the quantity of motion in the universe, and an equality in the original force by which bodies tend around their centers. The reason he gives us these hypotheses, as he clarifies in the next section, these few suppositions, those three hypotheses, seem to be sufficient for all the effects of this world to result from them in accordance with the laws of nature explained previously, as if they were the causes of these effects. And I do not think it possible to devise any simpler, more intelligible, or more probable principles than these, because no proportion and no order is simpler or easier to know than that which consists in equality of all kinds. And so from the three hypotheses in the remainder of part 3, he sets forth the sequence of those causes plus the laws of motion, or laws of nature, to the effects, to the world as we observe it. So what I want to bring forward here is this distinction, just to make clear what I see in Descartes' account. You have his hypothetical approach to the phenomena, or to nature. So we deduce phenomena from hypothetical causes. We describe how causes produce their effects in a mathematical sequence. This makes the phenomena intelligible to us, and the phenomena are thereby explained and very easily understood. This explanation, understanding, is contrasted with truth, as we just saw in just looking at the second passage. The truth is revealed by natural reason, and thus does not provide us understanding of the phenomena. It doesn't make the phenomena intelligible to us. For intelligibility, we need this sequence. Now, to characterize, this is on the bottom of the handout, so you can refer back to it, but just a brief characterization to help us see what I'm seeing in Newton. So Descartes' deduction from hypotheses, to propose causal explanations that do not conform to the truth of the natural world, but from which we can clearly comprehend a sequence of events that allows us to understand the phenomena we observe. And a lot hinges here, of course, on how he's using the notion of understand, because it does not require truth. And this is what I'm claiming is what Newton is trying to improve upon. For him, I mean, there are different ways of putting it. In its strongest version, you might say, for Newton, you cannot explain nature if you don't have a true account of nature. You need to have truth to have genuine explanation. So what we see, so the AntiCartesianism of Newton's view in the general Scholium, he contrasts his experimental philosophy, of course, with the hypothetical, and he names names in 1713 in the draft. In a letter he drafts to Coates, and he names Descartes and Leibniz in particular. So experimental philosophy reduces phenomena to general rules and looks upon the rules to be general when they hold generally in phenomena. Hypothetical philosophy, practiced by Descartes and Leibniz, consists in imaginary explications of things and imaginary arguments for or against such explications. This notion of imaginary, for me, I'm reading this, it is not proven in any way to be true of the natural order, which earlier in 1704, when he was writing a draft preface to the Optics, it makes Descartes' system a romance, a term used by Coates also and Voltaire later. But if without deriving the properties of things from phenomena, you feign hypotheses and think by them to explain all nature, you may make a plausible system of philosophy for getting yourself a name, but your system will be little better than a romance, and then that's from the original. The problem, as I see Newton, the problem Newton is trying to address. Descartes does not tell us what holds in the phenomena, what is truly the case in nature. He merely offers an intelligible system for organizing the phenomena, rendering the system a romance. So, my claim, with his experimental philosophy, Newton tries to improve upon Descartes' account of the visible universe by providing explanations that are true of the natural order, or again, you might recast this, by providing genuine explanations rather than romantic ones, all right? And so to do so, as we know from the rhetoric of the general Scholium, he's going to do this by replacing a deduction from hypotheses with a deduction from the phenomena, where, my claim, to deduce explanations from the phenomena is to rely on empirical evidence to establish the truth of principles that are rationally intelligible. Now, this might not seem all that controversial, but the claim, the more specific claim I'm making, which I already mentioned before, is the second point. He improves upon the hypothetical philosophy by relying on the empirical evidence to bridge the gap or fill the Cartesian gap between intelligibility and actuality, or more generally, between explanation and truth. So what I'm not doing is reading a deduction from the phenomena as an induction, which in some sense is what Shapiro does. And this is why he finds no evidence in the three cases for similarities. He sees induction in the case of Rule 3, but he can't see a generalization over empirical data in the other cases. And so then he says, see, they're not similar. But I think if we take this other approach, you can actually see a common thread. One more note now before turning to Newton himself. I still follow Shapiro in claiming that this is a slogan, and you might say some rhetoric about method. I don't think in the Principia Newton is showing us how he actually discovered these things. I don't think when he's presenting the laws, for instance, and you'll see in a second, I don't think he's showing us that this is how he actually came to discover what the laws are. He's doing something different that you might call heuristic, you might call rhetorical, but it's a strategy to convince the reader that he has found explanations that are true. And that's how I'm reading the text here. So, to be a little more specific now before getting to the three cases, Newton begins, in all three cases, this is what I'm going to claim. Newton begins with what is rationally intelligible, but mathematically certain for him. So he's using mathematics, of course. From this so-called Cartesian starting point, he relies on the phenomena to show that what is intelligible and certain applies to the physical system, to show, in other words, that what meets the standards of human reason is also true of the natural order. So let me fill in some of the blanks. Again, I'm going through the two cases, the laws of motion and the properties of bodies, and we'll skip gravity. How am I doing on time?
You're doing fine.
Great. All right. And here with the laws of motion, I'm going to focus on the first and the third. One, because these are the ones Newton himself says are grounded upon phenomena and are to be considered rational principles founded upon phenomena by induction. But I'm also focusing on them because, as you all know, these are the two cases in which he mentions empirical evidence in the discussion that follows each law. So, case of law one, we have the law of inertia, right? And then we have mention of projectiles, spinning hoops, and planets and comets. I'm not going to read through all of this. I assume it's a reminder. And then in law 3, we have action-reaction, and then we have mention of pressing a stone with a finger, a horse drawing a stone with a rope, and then a body impinging on another. Question or problem, and this is something that Shapiro in his presentation alludes to, but it's been alluded to by several people. The problem with these empirical cases. If the laws of motion are founded upon phenomena by induction, insofar as they are generalizations based on empirical evidence, then it's not clear how Newton can justifiably term the laws axioms and use them as propositions upon which his mathematically exact system of rational mechanics is founded, right? So these are axioms or laws, but by some one reading you could say, but he's using empirical evidence, so it doesn't seem he has the right to call them axiomatic, right? They should be accepted without proof. So here's what I'm offering as a reading of the laws. They're to be accepted as mathematically certain, independent of empirical evidence. Phenomena enter the discussion to show that these mathematically certain laws are true of all bodies in the physical system. In other words, it's the application of mathematically certain laws or axioms to nature that is grounded upon the phenomena. Now here, where's the evidence coming from? The Scholium. I'll skip that. The Scholium to the laws of motion. Now, the first sentence of the Scholium, the principles I have set forth are accepted by mathematicians and confirmed by experiments of many kinds. And I'll just read the whole passage. By means of the first two laws and the first two corollaries, Galileo found that the descent of heavy bodies is in the squared ratio of the time, and that the motion of projectiles occurs in a parabola, as experiment confirms, except insofar as these motions are somewhat retarded by the resistance of the air. Now, here, there are different ways, and I actually could have underlined this other part. In the red, I'm highlighting the difference between how he talks about what is mathematically founded or mathematically demonstrated and the role that experiment plays. And if you look throughout the Scholium, there is a consistent way in which he talks about math on the one hand and experiment on the other. So here we have principles accepted by mathematicians and then confirmation by experiment. And if you continue, oh, that's supposed to be red, sorry. You have what is demonstrated mathematically by a theory of pendulums or by the theory of oscillations, and also later in a moment you'll see by the theory of impacts. You have what is demonstrated and what is found by mathematicians, and then you have what is supported by or confirmed by experiments later done or later completed. And here, this comment about Wren, Wren additionally proved the truth of these rules, the rules of collision, before the Royal Society by means of an experiment with pendulums, which the eminent Marriott soon after thought worthy to be made the subject of a whole book. Again, if you look at how it's worded, there's a consistent difference here. There is what is mathematically demonstrated and acceptable and certain, and then there is the use of experiments to prove the truth. Now, it's not, of course, that experiments make mathematical claims more mathematically certain. They're mathematically certain independent of evidence, right? They're accepted by mathematicians. What the experiments do, what the empirical evidence does, is explain or prove, to use his rhetoric, the applicability, that these are mathematical principles that do hold in nature itself. It's bridging the mathematically certain with the empirically real, as it were. And so some other examples also from the Scholium to the laws of motion. The rule which the experiment was designed to prove, the rule is tested in bodies. I have tested this as follow with tightly, oh sorry, I said wound, that's a typo, balls of wool. And then the third law of motion, insofar as it relates to impacts and reflections, is proved by a theory of impacts and collisions, which agrees with experiment. So again, looking at the way these words are used, demonstration, tested, I'm just going through this quickly, and here's the summary. On the one hand, mathematically certain principles, they're a certain class. The axioms or laws of motion fall under this grouping. They're accepted by mathematicians. They're demonstrated. You have the rules of collisions and impacts, where he presents the experiments from pendulums, but the rules themselves were founded by the foremost geometers of the previous generation. And then the empirical evidence confirms, supports, proves the truth, and allows us to test the theory. Again, difference between mathematical certainty on the one hand and support of its applicability, the applicability of the math to nature. So, in the Scholium to the laws of motion, empirical evidence using Newton's terms proves, confirms, supports that demonstratively certain laws and rules capture how physical bodies behave. In this sense, the phenomena serve to justify the applicability of mathematically certain and rationally intelligible principles to the physical system. In other words, the phenomena bridge the mathematically certain and rationally possible order of things to the empirically actual state of affairs. So to bring us back to Descartes for a moment. As Descartes, Newton begins with principles, laws, and rules that meet the standard of human reason, where here Newton is using the model of mathematics. For Newton, the principles are rationally intelligible insofar as they have been mathematically demonstrated. However, Newton improves upon Descartes' hypothetical approach to natural philosophy by relying on experimental and observational evidence to fill in that Cartesian gap between intelligibility and actuality. Now, just a note, which I'll come back to later, I think, if Newton didn't do this, if Newton simply gave us mathematically demonstrated principles, he would, like Descartes, have a romance on his hand. He would simply be giving us principles that meet the standards of reason without any evidence, whether it's proof, whether you want to follow his rhetoric. He wouldn't have any way to convince us that they are true of nature itself. They would simply be rationally intelligible. Now on to what is probably the hardest case for me to make in the last 8 or so minutes here. Rule 3. So I want to give the same story, but of course, it'll be that the evidence for the story I'm telling in this case will be a little different. This is the locus classicus for reading deduction from the phenomena as an inductive generalization over empirical evidence, right? The way that Newton presents what the qualities of bodies are, we have him claiming the qualities can only be known through experiments. Qualities that square with experiments universally are to be regarded as universal. And if we continue, I've highlighted all these passages that people like Coates in particular focus on to describe or capture what deduction from the phenomena is as some sort of inductive generalization. And maybe here in particular, the third bold-faced statement that all bodies are impenetrable, we gather not by reason, but by our senses. So here there seems to be a sharp contrast. There's how we reason about bodies, and there's how we learn what bodies actually are, and that's through the senses. We can't rely on reason to know how bodies in the world, which properties bodies in the world actually have. So how am I going to make my case? By drawing on a paragraph or a few sentences here that someone recently told me is Newton's dumbest argument, but I think it's his, so that I have on my side, it's his argument, and I think it actually helps us understand what he's getting at in Rule 3. This comes at the end of the discussion, at the end of the first paragraph after Rule 3. From phenomena, we know that the divided contiguous parts of bodies can be separated from one another. And from mathematics, it's certain that the undivided parts can be distinguished into smaller parts by our reason. But it is uncertain whether those parts which have been distinguished in this way and not yet divided can actually be divided and separated from one another by the forces of nature. So there's what we can think about bodies, and there's the way that bodies actually are. But if it were established by even a single experiment that in the breaking of a hardened solid body, any undivided particle underwent division, we should conclude by the force of this third rule, not only that divided parts are separable, but also that undivided parts can be divided indefinitely. Now, you might already see how this connects with my reading. There is, on the one hand, the mathematical conception of body, right? And we can even draw back to book 1. You start with a mathematical notion of body where you simply have mass associated with it. What we're doing now here, we start with what we mathematically think of body, and our job is to determine which of those properties actually hold in nature. So there's a mathematical conception and then the real conception, as it were. And this fits with other things he says about thinking about things from a mathematical point of view versus a physical and true point of view or physical sense. There's the mathematical view of body and then the true and physical. And given where this comes, so remember going back to rule 3, thinking about where this is placed in the text, it's the point at which he is, to use his phrase, coming down to physics. And the job here, and this will link to gravity, but not right now, the job here is to take what we have mathematically demonstrated and compare it to the phenomena to figure out what is true of nature, right? Or what holds in the natural order, to put it in different ways. And I'm claiming he's doing the same with the notion of body. He's starting with a mathematical conception and using phenomena to figure out which of the properties we mathematically conceive are actual in the physical order. So thinking of it this way to try and schematize it, we start to the left with a mathematical view. We have properties that are intelligible to us that include all the ones he establishes, plus infinite divisibility, which he mentions. The question is, which of those belong to the real bodies outside of reason or outside the mind, however you want to put it? The way you do it, the way you figure this out, how do you select which are the real properties as opposed to simply the intelligible ones? You make a comparison with the phenomena or with experiments. So, experimental and observational evidence serve to justify, as I'm saying here, the applicability of mathematically certain and rationally intelligible properties to the bodies that populate the physical system. Or to put it differently in the way I've put it before, the phenomena bridge the mathematically certain and rationally possible order of things to the empirically actual state of affairs and thereby indicate what is true of nature and natural bodies. How much time? 2 minutes, great. So just to tie this back together, I obviously didn't do the law of gravity, but again, my reading of these 3 cases, if we look at the phenomena as this bridge, we see 2 things. We see the similarity with Descartes. We start with what is rationally certain, but we have this extra function or role ascribed to the phenomena. For Descartes, phenomena were simply that which was to be explained, the effects of some causes we were trying to identify. But for Newton, he gives them this additional role of being able to prove to us, convince us that what we are saying is intelligible is also actual. And so this is on the bottom of the handout. This is how I'm understanding this difference between Newton and Descartes and how I'm understanding the deduction from the phenomena. Remember, for Descartes, we have explanations without truth. We have intelligibility without truth. But for Newton, what he's trying to do here with this claim, according to his program, is establish causal explanations that are intelligible and that also conform to the truth of the natural world. So, as I've tried to point out, he's relied on empirical evidence to establish the truth of principles that are rationally intelligible. Thanks. Let the games begin.
All right, 15 minutes for questions. Let's start here.
Thank you, Mary, for your informative and careful paper. I just want to make one semantic point.
Please.
And you find that both Descartes and I think Newton's following him here use 2 key verbs talking about getting something from phenomena. They say getting from. One is deducere, and the other is colligare. All right? Desmond Clark, the Irishman, has written penetratingly about deducing, the use of that verb, deducere. But Caligari is rather different. It's a looser arrangement to the phenomenon. It means something like collection or gathering. Okay, so I think you ought to sort these verbs out a little bit in some of these contexts, and then I think you should disarm the reader once and for all.
Disarm what? I'm sorry?
Disarm.
Yeah.
Because people have the idea that deduction is something formal. Okay, mathematical
I
or
see,
formal. Now, in the 17th century, that was not the case.
Yeah.
That conception of deducing was certainly not there. All right?
Yes, thank you.
So these are just small little points.
Yeah, thanks, Ted.
Yeah, thank you. That was indeed very interesting. I have a question. You can hear me? Yeah. I have a question and a remark. The question is, I remember, it's a long time ago, there is a paper by Cohen, I think, on this third hypothesis in the different printings or in the different versions of the Principia. You choose one, I think one of the later, if I remember well, the first one in the first edition of the Principia had to do with this divisibility issue, but then from the point of view of physical property of bodies. And I have the feeling that it's a bit too, yeah, of course in the talk it's difficult to treat all this, but I have a feeling that you should take this into account into your justification, especially because it seems to be that the problem of the material divisibility, which of course touches to all the debates which have been referred to here already by many people, that it receives a specific kind of solution, if you want, by Newton, by bringing it up to the mathematical level, but I think you should take this into consideration into your analysis of this whole problem. And a second thing is, of course, that you saw yourself the word indefinitely divisible at the end of your crucial quote there, indefinitely being precisely the word that Descartes did use when he talked about certain types of infinity, and which Newton on other occasions says that he rejects explicitly. So I think there must be some little problematic topic to be treated as well. Thank you.
In this passage? The part,
Yes,
so,
there.
right, we don't know it's infinitely divisible.
No, I know that.
Oh.
But the point is, there is a lot of reasons to think that Newton rejects explicitly this notion of indefiniteness as a kind of replacement for infinity in a lot of contexts, especially the mathematical one. So I think it's a bit difficult to just pass over it. There should be some thought be given to his...
Yeah, so what I was trying to bring out, and sorry, maybe this will help. So I could have, I suppose, put here tentatively indefinite divisibility, right? From a mathematical standpoint, we do have infinite divisibility. Is that, and then you're saying, and the indefinite only gets ascribed to bodies. Did I miss your point? I'm sorry.
That's not what the point is. Oh. The point is that Newton objects to indefinite full stop. He objects to the concept of indefinite.
Oh, I see.
Full stop. So
On several occasions.
Yeah.
That's the point I'm saying. I'm not saying I agree.
Right. So he does in the case of God, right? That we can't say God is indefinite. But I'm not sure the other cases then, now that I understand the point, thank you, that he objects to the use of indefinite. I mean, if you look at I think it's on Andrew's handout, about there's certain cases when you do say indefinite, and that's when we can't complete the sequence, right? It's
Yeah,
when,
of
and
course.
so this would be that case, right? Based on the experiments we have, we can't yet prove infinite divisibility.
But
That is
okay,
holds.
but there you have this intermingling of the mathematical and the physical point of view. That's actually what I wanted to bring out. There is something problematic there.
Okay.
Okay, I've seen 4 hands, I think. Run.
Thank you, Mary. That's great. Just as a follow-up to Well, let me just begin with a very quick question. On this reading of things, and this may sound like a Newton 101 question, but is gravity deduced from the phenomena?
Yeah,
Okay.
on a similar kind of reading, I will.
Okay.
Yeah.
Because just to follow up on Ted's point, there's an interesting inflection to the word deducere that I've been thinking about recently in context of Bacon, who uses deducere from the legal context of making that which is invisible visible, making that which is not, and it's from the law courts. It's bringing out you've got to torture the witness to bring out what's really hidden in their thinking. You've got to bring them literally out of obscurity into the presence of the court. But you've also got this sense, he uses it very explicitly, instantia deductoria in Novum Organum, Book 2, to talk about bringing into manifest visibility, and he literally means sensible visibility in that sense. Sensibility, that's not visual, sensibility, that which is invisible, right?
Yeah.
And so there's a certain sense, you might say, in which gravity is, in that sense, not directly sensible, but it needs to be inferred, deduced from the phenomena, right? It's not itself a phenomenon, if I may put it that way.
Well, gravity is true. I mean, yeah, it's not a phenomenon, but it's a law, right? So he says the law.
Yeah,
of
I know,
gravity,
but I think this. I'm just giving force to Ted's point that in terms of moving from. Okay, I've made my point. The second thing I just wanted to say is that I think that this, and this is something that you know very well as well because you've read Barrow on this, but there are people working in the context prior to Newton who are thinking about problems in mathematics precisely about with having to do with the connection between that which is conceptually thinkable and that which is actually true in the practice of mathematics. And in Barrow's lectures, for example, to pick one, he solves all kinds of problems with respect to conceptually difficult questions with respect to, well, mathematicians actually do this, right? And so I think there's a more room there for thinking about how that kind of literature is actually informing Newton, and that's to add really strength to your point that this is on his mind, and I think this is. I mean, there's an old story about how people like Barrow affected Newton, but I think there's a new way to come at this, and I think your paper is giving a new life to that kind of genealogy. Thank you.
Yeah, thank you. I mean, I guess just a quick comment. The broader question that you're pointing to when I'm doing this, from the mathematical to the true. The other question he has to answer is, why are we justified in using mathematics at all, right, as a way to understand? And that's the sort of debate and issue that you're trying.
A very quick comment here, and then gentleman with the sunglasses.
There's a question about what I've called in one of my papers, atoms in the analogy of nature, transduction, where you go from a macro realm to the invisible realm. And that adds to the whole analysis, I think. I think you should consider that, because you're not straightforwardly deducing or gathering from the phenomena in the same sense.
In the same sense as?
When you're moving from macro phenomena.
Oh, right, yes,
I think
right.
Those distinctions have to be made.
Yes, yeah.
Yeah, so thanks a lot, Mary. There's a lot that this provokes. One thing that I think is subtle here is the characterization of phenomena and how that might be different between Descartes and Newton. So what's actually called phenomena in the second edition are the approximately Keplerian motion of the planets and the satellites.
Right.
So you already have something that's a mathematically characterized regularity that is the phenomena, whereas the phenomena that Descartes is giving explanatory hypotheses for do not have the same character. And so related to that, it's always been unclear to me exactly how to characterize the discussion in the Scholium after the laws, given that the laws are in some sense almost too abstract to have direct empirical confirmation. It's rather that you have to have an understanding of how the laws apply to a particular system, which involves all kinds of assumptions about the forces that would be in play in order to see them as being verified by the behavior of that system. Let me put this, so I guess I should actually come to a question. There's a sense in which another point is just that the context of this discussion in the Coates correspondence I think actually brings this out, because of course, Coates writes to Newton that he's working on the preface, and he comes to a problem in actually applying the third law and saying that not only is the sun acting on a planet, but that the planet would have then a gravitational force acting back on the sun, which involves the application of the third law to non-contiguous bodies. And when Newton actually adds to the Scholium of the laws in order to address this issue, it isn't a direct empirical confirmation. It's rather what he shows is how the third law relates to the first law. And he says, if you imagine the Earth and you imagine cutting it into two pieces, if the third law didn't apply between those two pieces, so that the pieces didn't attract each other equally and opposite, then the Earth would accelerate off, or any closed body would accelerate off to infinity, violating the first law. So the way in which he's giving an argument there is sort of the consistency of the laws among themselves. And that's his direct reply to Coates's worry, right? So I think the way in which you can see these as empirically confirmed is a bit subtle. So I guess that's the worry. But again, I guess I didn't really come to a question. So
well, you raised a lot of questions, but because you're pushing me on the point of how I'm reading apply here, right? When I'm saying that to deduce is to justify the application.
Right.
And then there's, the trickier problem of how do you actually take these laws and apply them to a given physical system. So I'm using apply in what you might think of as a looser sense, to say that, not that I can solve every natural problem or empirical situation that you give me, but that these, and this is something Shapiro himself points out, these are cases that illustrate the law, right? If you even look at the kinds of empirical situations we get in the text, it's a part of Newton saying, it seems like, so Shapiro's point is, we want induction, but we don't get it. What we get are these cases that seem to explain better to us what it would mean for this law to be a natural law, not just an axiom or mathematically certain law. So I think what you bring up is a different sense of application, right? Of how do you actually now plug in variables from the physical system to get these to compute, to get measurable data or so. Does that make sense? So I'm arguing for a looser sense that these are just ways of him saying this should be mathematically certain to you, but you should also be convinced that this is going to be the basis of a mathematical natural philosophy, is maybe another way to put it.
Yeah, if I don't know everybody's name, another question in the back.
Sorry. That's Eric.
Thank you, Mary. I think you really have advanced the discussion here over Shapiro for sure. I have two objections and they're related, but I don't think they're knockdown objections. I just want us to get clear. So I think you equivocate between the mathematical and the rationally accessible or rationally intelligible. And that's clear if you go back to your list on the third rule of reasoning. Impenetrability is not really mathematical, right? And hardness is also not really mathematical. So there's the status of some of these things is dramatically different. And that's part of Chris's point about the fact that the laws are about quantities and measures of quantities and have, as it were, applicability built into them if we have measures. That's not so clear on this list. So there's going to be a dramatic, even in your loose notion of applicability, there's going to have to be a distinction here. And that connects to my second question, which is why I'm going to ask it immediately after it. Is one thing that I think is really interesting and surprising about this symposium, together your paper and Andrew's, and maybe I should have realized this after reading Guicciardini's books, but both of you are arguing basically Newton is not an empiricist about geometry. Geometry turns out to be almost Aristotelian-like, or maybe Hobbesian-like, the art of the possible, and not the art of the real. To me, this has come as a shock, and I know Nikolai probably should not have been shocked, but it really is. Because, and here's, I think, the pressure, if you go back to the preface to the reader of the Principia, Newton says geometry is founded on mechanical practice. And it doesn't look like to be only a science of the possible, but a science, and then it's made exact, etc.,
Yep.
all that. So it seems to me either the two of you, and I also include Andrew in this, are exposing a real tension in Newton's philosophy of geometry in the Principia, or there's a real objection here, connected, I think, in part to this main point, namely that if you're dealing with quantities, you have, in a way, certain easier access to the world than not, right? But these are distinct issues. There can also be imaginary quantities, obviously.
So I could let Andrew answer since we're both targeted here. But so my view about the geometry and the possible and actual, I think it is a science of the actual form of space. But now we're talking about body, and we're talking about things which we don't know, right, essentially, or however he puts it in the general Scholium, right? We can't know the inner substance of bodies. That's something we can't know. We can't know about bodies except through the senses. Geometry, though, I take to be a science of actual space, the same space that is used in the mechanics and the same space in which motion, through which motion occurs. So I think there is an actuality that goes along with the geometry, but not when it comes to body. That's something we can only know through the senses, but know in this more complicated way, right?
Extract from the senses by your own reading. I mean,
Yes.
I'm doing a Dimitri here.
Which page? Yeah.
That this is abstraction. This is
Yeah.
not senses.
This is, say the last sentence.
The application here of geometry is an issue of abstraction. We're not really dealing with.
No, but the source of our idea of space, right? It's not a priori. It's not an innate idea. We have to get the idea of space from somewhere. But once we're reasoning about space, then you're doing what you might call abstract mathematics, right? There's a story I tell about where the idea of space comes from, but doing geometry is then doing a science of this ideal form of space.
I'm talking about mechanics. I agree. But I think that geometric mechanics, to use two words not together, that don't belong together, I took it that on your reading of the method.
Of math?
Of Newton's method, and of applying math.
Yeah.
We don't have a gap between the world and mathematics.
Insofar as geometry deals with the same form of space that is the actual form of space.
The entities are geometric entities that we deal with.
In book 1 and 2. But now we're transitioning to physics, right? We're transitioning to bodies that have more properties than mere mass and mobility. And
Sorry.
We have time for one more question, I think.
I don't think you can sustain that reading of book 1. There's plenty of actual entities in book 1. Just read the Scholium at the end.
Okay, this is very, I agree with Eric that you advanced the discussion over Shapiro. I'll defend one thing you said very briefly, and then just one question. I think you're right. I wouldn't put in infinite. He says indefinite, and in that one respect, it's a possible process, right? He accepts the idea of the indefinite, as we saw, in the case of possible processes. He thinks Descartes' wrong to apply that to anything that's actual. And we're talking about a possible division. So that fits. I think you're absolutely right about Rule 3 in that regard. And that's really interesting. Okay, back to the passage about Galileo. By means of these first two laws, Galileo. Okay, yeah. This is a very hard passage to understand for anyone because historically this is problematic, as everyone knows. Galileo did not have the first two laws of motion in any obvious way. And one way in which he didn't is that unlike Descartes, who took the first two laws of nature to be very general and applied to motion in a very general way, Galileo seemed to be thinking about what we would call inertia in a more restricted fashion.
Right.
There's some great work on that by David Miller and others. So I wonder here, is Newton, and this is just a question for you, is Newton signaling that he's not following Descartes on the laws of motion, by saying something that is a little problematic and attributing them to Galileo. Since, of course, the principle of inertia really should be attributed to Descartes in its full generality, even though Newton, of course, uses impressed force and has a different way of thinking about it. By saying that it's Galileo who used these first two laws, which is highly problematic, is Newton saying, I am not following Descartes, not in the content exactly of the laws, because Galileo doesn't have the content, but methodologically. That is, Descartes, of course, deduces the laws from the immutability of God. Clearly, Newton is methodologically rejecting that as a possible way of thinking.
Right.
Instead, by attributing to Galileo, is he saying, well, methodologically, really what we should be thinking about more is experimental evidence for generalizations. I think it's just a challenge to an otherwise very convincing story that you've presented about the mathematical certainty of the laws. There's still a question, why call them axiomata sive leges motus? That's hard for all of us to figure out exactly. But in this passage, I do wonder if he's signaling a methodological difference with the Cartesians.
Well, I mean, there's a lot built into the rhetoric. I mean, and so it is the rhetoric of the presentation I'm trying to unpack. But what you said sounds persuasive. He's ascribing to Galileo a law he never had. He had circular inertia, and he didn't have rectilinear inertia as we know it. So, but when you said, is he signaling a methodological difference with Descartes, you mean insofar as these laws for Newton are not metaphysically deduced? So I guess it doesn't quite fit with what I'm saying here, because what I'd want this to say is what Galileo did was reason first in that sense, yes. But Galileo first reasoned mathematically and then turned to experiment for confirmation, or we turned to experiment for confirmation. So yes, I mean, he's not, yes and no, right? I mean, so he's not saying, yeah, the laws come from God, or thinking about God's nature. So it would be odd to put Descartes in this context because his laws were not treated this way. I agree. I'm not sure how much help it gives the reading, but it's certainly consistent with the reading I'm offering, yeah.
Okay, I think we're out of time. I can continue things over lunch, however.
Thank you.